Hello all. We know that when a system absorbs energy, it goes to higher excited state, but then it doesn't remain there in the excited state, it comes down to the ground state. Now, we have seen that there are various ways by which the absorbed energy is dissipated by the system. Now, there are radiative transitions and non-radiative transitions. In my earlier video, I had briefed you on non-radiative transitions like internal conversion, vibrational relaxation, and intersystem crossing. Now, in this video, I'll brief you on one of the radiative transition, that is fluorescence. The other radiative transition is phosphorescence, which will be dealt later. Now, we are familiar with Jablonski diagram, which depicts the energy transitions when a system absorbs energy or absorbs photon. The energy transition between various electronic states can be depicted using Jablonski diagram. Let us see how fluorescence can be explained using Jablonski diagram. Now, these are the various the electronic states. Here you have the S0, that is the singlet ground state. You have S1, that is the first excited state. S2, the second excited state. S3, the third excited state. And all these bold lines are the lowest vibrational state of each electronic state. And these lines, lighter lines, weaker lines, are the vibrational levels. Okay, so every electronic state will be having vibrational levels, and we have seen that as you go higher, as you move on to higher excited states, the band gap, energy gap between the electronic states comes down, is minimized or is lowered, and the vibrational levels tend to overlap. Now let us see what's happening during fluorescence, or what happens during fluorescence, or what are the energy transitions that happens during fluorescence. Now when the system absorbs energy, it moves on from the ground state to higher excited state. Now here we have depicted only the singlet states, depicted as S0, S1, S2, S3. That means the electrons in the system, the spin of the electrons, the system is not changed. The spin multiplicity remains the same. Okay, so the system absorbs energy. It moves on to higher excited state. Now here the higher excited state to which the system has reached is S2, the second excited state. From there, it will not remain there, it will come down to ground state, and there are various ways by which it can come down to ground state. One of the ways is first via internal conversion, that is, the system from the vibrational levels of a higher excited state comes down to vibrational level of the next lower excited state. Now even here the electron or the system is at a higher energy level, so it comes down again to the lowest vibrational level of the first excited state. That is called vibrational relaxation. So the first one, that is between the transition or energy transition between the higher excited state to the vibrational state of lower excited state, is called internal conversion. That is without radiation. It is in terms of, the energy is transferred either as heat or as by transferring the energy to neighboring molecules. And from there again another non-radiative transition, that is vibrational relaxation. Now another possibility is that the electron moves from the ground, or the system moves from the ground state to the higher vibrational level of the first excited state. From there, from the higher vibrational level of the first excited state, it comes down to the lowest vibrational level of the first excited state via vibrational relaxation. These two are non-radiative transition. Now, once the system reaches the lowest vibrational level of the first excited state, it comes down to the ground state by emission of radiation, and that is fluorescence. So, fluorescence happens between, or is the energy transition between the ground state or the lowest vibrational level of the first excited state to the lowest energy vibrational level of the ground state, or to any of the vibrational level of the ground state. So here you can see that it is going to the first vibrational level of the ground state. These two, it depicts the fluorescence. So it is between S1 and S0. Okay, and fluorescence is a comparatively slower process when compared to internal conversion and vibrational relaxation. It takes around 10 to the power of minus 9 to 10 to the power of minus 7 seconds only. So immediately when you, when you irradiate the system, it immediately fluoresces if it is a fluorescent material. Alright, so the fluorescence is seen immediately within no second of irradiation. And also fluorescence is a spin allowed transition, or it is an allowed transition because the spin multiplicity is not changed. And the energy of the fluorescent radiation is equal to the energy gap, or the energy difference between the lowest vibrational level of the first excited state and the various vibrational levels of the ground state to which the molecule falls. Okay, now if the molecule comes down to the higher vibrational levels of the ground state, it will come down again to the ground state, lowest energy level, vibrational level, by vibrational relaxation. That is a non-radiative transition. Now there are the various, we can say that there are, the pathway of fluorescence can be depicted like this. The molecule or the system absorbs energy. It undergoes energy dissipation, or some amount of its energy is lost by internal conversion, and then again it is lost by vibrational relaxation, followed by fluorescence. So that is this: absorbance, internal conversion, vibrational relaxation, fluorescence. Or absorbance, vibrational relaxation, and then fluorescence. So be it the first pathway or the second pathway, we find that the energy of the fluorescing radiation will be less than the energy of the irradiated light. So that is the fluorescent wavelength, energy will be less than the irradiated energy. So EF is less than EI, fluorescent energy, or the wavelength of the fluorescent radiation will be greater than the wavelength of the irradiated radiation. We can say incident radiation. Alright, so this is the case. This is a simple depiction of the various energy transitions happening, which results in fluorescence. Okay, so this is the Jablonski diagram. Now that was when a system has vibrational levels, etc. And in the case of atom, it is different. Atoms do not have what we call the vibrational levels. So in the case of atom, the wavelength of emitting radiation will be equal to the wavelength of the exciting radiations, since there are no vibrational energy levels. In the early case, we have seen the wavelength of the emitting radiation will be greater than the wavelength of the exciting radiation, or the reciprocal if we are talking in terms of energy. Okay, because some amount of energy is lost during internal conversion and vibrational relaxation. But in the case of atoms, we don't have so. The wavelength or the energy of emitting radiation and the energy of the exciting radiation is the same. And that is called resonance fluorescence. Atoms like sodium vapors, mercury vapors, etc. exhibit resonance fluorescence. There is no loss of energy. Alright, and also fluorescent emission stops as soon as the source of excitation is removed. So you find fluorescence only when you expose the material to light. Once you remove the source of excitation or source of radiation, then fluorescence stops. I give few examples. One of the examples is quinine sulfate. When it is exposed to UV visible light, it gives bright blue fluorescent light. It fluoresces. But once you remove the light, it will not emit light. Okay. Similarly, alcoholic solution of chlorophyll. This particular material, you can try it out in your lab. You take chlorophyll, alcoholic solution of chlorophyll, and then irradiate it with UV visible light. You get deep red color. It's easy. You can do it in your lab. And then substances like fluoride, riboflavin, petroleum also fluoresce when exposed to UV visible light. And then vapors of sodium, mercury, vapors of acetone also exhibits fluorescence. Okay, so fluorescence is an instantaneous process. We can say that when it is simulated by light or irradiated with radiation, the instant emission of radiation, that phenomenon is called fluorescence. It happens between the electronic states S1 to S0, and also it happens within a short span of time, that is around 10 to the power of minus 9 to 10 to the power of minus 7 seconds. Alright. So, hope you will remember these examples and what is resonance fluorescence and also the Jablonski diagram. Okay. So, if you have any more clarifications regarding this, please feel free to ask me. Thank you for watching this video. Thank you.